Hello and welcome. I'm Munindranath Durjashaha. On behalf of my team Hollow Purple, I introduce you our presentation topic, GNN Scheduler Co-allocation wire GPU cursor scheduling using graph neural networks. As AI models continues to grow, GPU cursors have become one of the most valuable computing resources. Modern schedulers try to utilize GPU utilization, but they often ignore how multiple jobs affect each other's performance while they share the same GPU. Our project introduces an intelligent scheduling system that predicts this interference before parsing a job, enabling smart GPU allocation while maintaining high utilization. Before explaining our solution, let's first understand the problem. We use official Alibaba GPU production trace, which contains more than 8,000 real GPU jobs. Interestingly, 43.6% of these job request functional GPUs, meaning GPU sharing is not an exception, it's actually common practice in production cursors. However, research from Horace shows that when two computer intensive jobs share the same GPU, their execution can become up to 3.2 times slower because they compete for the same hardware resources. The problem is that current schedulers like FGD only evaluate each GPU independently. They check available resources but completely ignore interactions between co-located jobs. As a result, the schedulers may choose a placement that looks optimal on paper but causes significant performance loss in reality. To overcome this limitation, we designed a hybrid three-component scoring system. The first component is fragmentation, which uses FGD's original mathematical formulas to measure wasted GPU capacity. Since this is deterministic, so no machine learning model is required. The second component is interference, which is the only learned part of our scheduler. Here, an aged wire graphical neural network predicts the slowdown that may occur if a new job shares the GPU with existing job. The third component is expected utilization, which is calculated directly from the current cursor state. Finally, these three scores are combined into a weighted scheduling score. Our philosophy is very simple. We only want to use machine learning where traditional formulas are insufficient. Now let's see how the scheduler works internally. The pipeline starts with feature engineering. For every incoming job, we collect node features such as GPU utilization, memory usage, runtime, priority, and GPU type. We also compute edge features describing relationships between jobs, including GPU overlap, memory overlap, runtime overlap, and priority differences. Next, we construct a co-location graph where each node represents a job, each edges represents a potential interaction between jobs sharing the same GPU or not. This graph is then processed by a edge-aware GATP2 graph neural network, allowing the model to learn complex relations between neighboring jobs. Finally, the network produces three outputs: fragmentation, predicted interface, and expected utilization. In the second half of the pipeline, these three outputs are normalized and combined using weighted scoring equation. The scheduler evaluates every candidate GPU and selects the placement with the highest overall score. After making the scheduling decision, we validate the model through multiple experimental stages to ensure every improvement is significantly justified. Finally, we map scheduling improvements into meaningful real-world metrics such as reduced fragmentation, lower interface, increased utilization, energy saving, and operational cost reduction. This allows us to connect traditional improvements directly to measurable cursor benefits. The obvious question is, why use a graph neural network? The answer lies in the nature of the problem. Fragmentation is an individual property of a GPU, so traditional mathematical formulas work perfectly. Interface, however, is fundamentally different. It exists between two jobs sharing the same GPU, making it a pair-wise relationship rather than an individual property. Graphs are normally designed to represent relations And our model also incorporates edge features such as GPU overlap, memory overlap, runtime overlap, and priority differences. Unlike Graph Sage, GATV2 Convo can directly utilize these edge features, making it much better suitable for predicting GPU interfaces. To ensure our evaluation is reliable, we designed a four-stage validation strategy. First, we reproduce the official FGD results using the original simulator and Alibaba trace to establish a trustworthy baseline. Second, we improve only the interface formula while leaving everything else unchanged. Third, we replace the synthetic interface estimate with our graph neural network. Finally, as an optional extension, we plan a live adoption experiment where the scheduler continuously updates its predictions while replaying real workloads. Since each stage changes only one variable, any improvement can be clearly attributed to that specific modification. Based on literature collaborated simulations using Alibaba Production Trace, our scheduler has the potential to significantly improve GPU efficiency. The projected results indicates reduced interference, improved GPU utilization, lower energy consumption, and lower operational cost. For large GPU cursors, these improvements could translate into thousands of dollars in weekly saving while also reducing electricity uses. It is important to emphasize that these numbers are simulated based on projections collaborated using published researchers rather than just measured from a live production cursor. Our implementation uses a practical and reproducible technological stack. The scheduling logic and machine learning pipeline are built on using Python 3.11. The graph neural network is implemented using PyTorch and PyTorch especially the GATV2 Convo architecture. For evaluation, we use the official Alibaba GPU production trace containing over 8,000 real jobs collected across 1,213 nodes over 149 days. We use React to create an interactive visual dashboard while Docker ensures a reproducible simulation environment. Finally, Git and GitHub supports collaborative set development and version control. The entire project can be run on standard student laptop without requiring any specialized hardware. Now here we compare our schedulers with existing approaches. The traditional schedulers such as FGD and BestFit optimize resources low allocation but cannot model interference between jobs. Research systems such as Orion and Horace can detect interference, but they require kernel modifications and runtime profiling, making the development much more complex. Our scheduler predicts interference using a graph neural network while remaining deployable as a standard Kubernetes scheduler extensions. Rather than relying on existing schedulers, we enhance them by adding an intelligence layer that allows better replacement decisions without changing the operation system. To conclude, our project is more than just a research idea. We already have a working implementation using official Alibaba simulator and production trace. Our evaluation is fully reproducible because every experiment is performed using publicly available dataset and benchmarking tools. During the demonstration, judges will be able to observe the scheduling decisions, graph construction, and performance metrics updating in real life. We believe our project combines technological innovation, real world applicability, significant evaluation, and practical deployment, directly addressing the judges' criteria that has been addressed in Hackathon. And this is all for us. Thank you so much for your time and consideration, and we would love to answer any question that you have.